Today we're going to continue with our discussion of this thing. Does anybody here have a piece of gum? A piece of gum. Can you give me a piece of gum, please? I prefer a new one, yes. Okay, I'm going to play some music for you while I write on the blackboard, which was written last time. It's one of my favorite songs. Okay, for those of you who are paying attention, the lyrics of that song will help you solve many homework problems. Now, for those of you who weren't, you missed the big message. Yes?
Maybe we can turn off the sound system or something. There's this loud buzzing right there.
Sound system stinks. The sound system is really bad. Not only that, I think it's only getting the left channel. So the words, which were the moral of that song, weren't really coming through. So we should check the sound system. Anyway, okay, so for those of you who are annoyed by the buzz, or the left channel not coming through strongly, the keywords in that song were let x equals x, which is a key way to solve problems, all kinds of classes. You think of the same quantity two different ways, and it tells you something about the various variables and different ways of thinking about them. Okay. This is really distracting, this gum. That's disgusting. What am I supposed to do with that? I'll put it over here. Garbage, I can't put it in the garbage. That's ridiculous. Okay. Last class we had this system here, which is meant to be a picture of this system here. And it's got this motor which turns this shaft around so that this position x0 goes like d sine omega t. And this is this Scotch yoke design. In some applications, this dot here is much bigger, and it's a little bit distracting because it looks like a wobbly disk, but it still comes out that you get just a sinusoidal motion out of this. Okay, given this picture and these free body diagrams, I'd like you now, without looking at your notes, to write down what we get for mass 1 linear momentum balance. Okay, so do not look at your notes and write linear momentum balance for mass 1. And let me give you a hint. Don't try to put all the distances and so on into it. Just write it in simple terms down here. Is that the sum of the forces is equal to the mass times the acceleration. This is the thing we call rate of change of linear momentum. And I have a minus T1 plus T2s plus T2 damper equals mass times x1 double dot. Okay, any questions about that? Okay, who got that? Okay, very good. So now you can write the second one down for mass 2, which is minus T2s minus T2 damper plus T3 equals M2 x2 double dot. And then we can fill in these tensions. This is the hard part, getting the signs right on these tensions. This problem, as I've set it up, is a little bit harder than the homework problem you're handing in today. Why is that? Because in the homework problem, we said that all of the springs were relaxed in the initial configuration so that all the springs just fit in place, unlike this machine where the springs do not fit in place. They're too short. They're all stretched even when this thing is still. So homework was a little easier. You could just measure things from that equilibrium position. Here we don't even know where the equilibrium position is, so we measure positions relative to the base. When in doubt, you want to do the problems this way. You can only do that shortcut that you can do in the homework due today if the problem is set up just so that you know the equilibrium position. Okay, so what is this T1? T1 is K1 times x1 minus x0. What is T2s? That's K2 times, and this was one of the hard ones. And what do we have to put? We have to put the length of the spring, which is L2, minus its rest length. And what is L2? It is x2. That's the position of the right end of the spring, minus the position of the left end of the spring, which is x1 plus w1. So this whole thing is the length of spring 2, and then we have to subtract its rest length. Okay, any questions about that? Same as last class. Similar to the homework. In the homework, however, you didn't have to deal with this rest length or this thing. All you had to look at was the change of length, which is these two things, the homework you're handing in today. Yes? Why do I need L1 not here? T1 minus L2. 1 naught. Why don't I need it? Because I don't know what I need. You don't know what you need until you're missing it. Yeah? Where, here?
Yeah, instead of x1 minus x naught minus L1L, can you just write x naught plus L1L?
No. So if you put this distance plus this distance, the rest length of the spring. Now the rest length of the spring is something like this. And that will only take you to here. Where this mass is not the rest length position, it's the current length position. So L10 is what you buy from the store. So for this spring here, this is the 0 spring. If I put x naught plus L10, that would take me to here. I want to know where it is now, which is x1 minus x0. That gives me this distance, but I wonder how much the spring is stretched. So I take that distance and subtract the length of the spring beforehand. Does that address your question? Okay, now the dash pot people had a little bit more trouble with, I noticed in questions. The dash pot, we get C2 times L2 dot. That's the rate at which this distance is increasing. It doesn't matter what the original length is. The dash pot just resists velocity, not position. So L2 dot is the time derivative of this whole expression. But the time derivative of this whole expression just says x2 dot minus x1 dot. This is C2 times x2 dot minus x1 dot. That's the rate of increase of the length between these two things. It only depends on the relative velocity. If V2 is bigger than V1, then the length is increasing. If V2 is smaller than V1, it's decreasing. If V2 is negative, it's decreasing, and so on. So the rate at which the dash pot is stretching is equal to the difference between these two velocities. And then T3 is K3 times the length of spring 3 minus the initial length. What is the length of spring 3? In this way of working things out, it was this x2 plus W. Write everything backwards. It's the L minus x2 plus W2. That's the length of spring 2. And then we minus L30. Sorry, the length of spring 3 minus L30. Okay, now what we're going to do with these is try to put them into MATLAB. So how we're going to put them into MATLAB is we're going to say x1 dot is equal to v1, x2 dot is equal to v2, v2 dot is equal to the sum of forces on v2, which is some big expression divided by m2, and v2 dot is some big expression divided by m2. 1 and 2. I had the 1 and 2 backwards. Somebody who's whispering, do you want to do that out loud, please? Whatever it is you're asking your friend, just ask it out loud. You'd be doing everybody a favor if you do. Okay. Yes, please.
Wouldn't you want to assign the x attribute?
Does the order of doing these things matter? Well, yes and no. In terms of numerical errors, it does matter. In terms of does it all converge to the right answer if you take a small enough step size, it does not matter. The easiest way to think about it is we have a collection of numbers. We're going to calculate all of their rates of change. We're going to use that calculation to advance all of them. Okay, that's the easiest way to think about it. If you do sort of 1 foot in each pot, this time you can actually improve the accuracy of some things by doing something like you said, but if you do it backwards, it'll make it worse. So it's easiest just to think We're going to predict the future by knowing the rules for how the future evolves. If we know all of these things, we can calculate all these rates of change, and we're going to do it like that. Does that address your question? Okay, so now we're going to think of this quantity z, and z is going to be this list of numbers, x1, x2, v1, v2. And then we're going to say that z dot is equal to some function of z, and maybe t, and maybe parameters. So this is, in this case, this is all the x's and the v's. This is all the k's and the m's and the c's. And this is time as you know it. So now we think of this, we can predict the future by using the laws of mechanics and the laws of geometry. If we know all the positions and velocities, we can calculate the rates of change of all those positions and velocities. And we can abstractly write this way. And then we can write z new is equal to z old plus z dot times delta t. So then this then tells us that we have Euler's method becomes a simple thing. We say z sub I plus 1 equals z sub I plus z dot times, I'll call this h, and h is delta t. And we make a loop. And we end the loop like this. And this then becomes Euler's method. We do that again and again, and we march into the future, figuring out how things will change for all time. And this is the way all dynamics problems are solved, except for this thing Euler's method in the limit corresponds to calculus, and there are tricks for algebra for doing the limiting case of this with sines and cosines and exponentials for some simple problems. But in general, this is conceptually what you're doing, even for those problems which you cannot solve for sines and cosines. The limiting case of Euler's method is more or less the definition of what a differential equation is. Any questions about that? Okay, so now we'd like to try to get this onto the computer. And I did some of the work ahead of time because it's tedious, but some of it I did not do, which is also tedious, but we're going to do it here now, if I can. Send to center display, lower the big screen, make it get somewhat dark in here. How's that? For variety in lighting. The front lights are on though still, they stink, right? That's too dark. House lights rear. It's those front lights I don't like. All right. So last time I had a. This is the last thing we did, which was forced oscillator. And remember, it's all this confusion. But after you stare at it for a while, it becomes unconfusing. And rather than stare at that one again, we're going to start with the new one, which I just started with that old one, and I clean it up for our purposes here. So what I'd like to do, though, is start with the part that I didn't clean up a little bit and jump right to the differential equations. That's the bottom of the screen. Everybody can see that? Okay, so the first thing is I've passed in all the parameters with a single variable p. So I don't know what this is called in MATLAB, a structure or something like that. But if I just invent, you can always go w equals 7, and it remembers w equals 7, and we can go x equals w. And then it remembers what x is. But now we can do this funny thing. We can go w dot m equals 7. Why didn't it like that? Did it get it? It got it. Okay, so I go w dot m equals 7, and I can go w dot k equals 11. And now it's got both of these things stored in W. So I can go x equals W. And now there's a new variable x. What is that x? X dot m is equal to 7. And x dot k is equal to 11. So it's a way of storing things. It's kind of like an array, but all the elements have names. And that's with this dot, x dot. What's that called in MATLAB? A structure? Or does anybody know what it's called? That's called a structure. But that way, remember when we were passing all these parameters back and forth, we had this giant list. We can just now call it P, and it all gets stored in one place. So over here we have this P, and we're going to assume that we've stored in P all the different things that we want. And we've stored them rather than as a list, 1, 2, 3, 4, 5, 6, 7, 8, 9, that we have to remember. We've stored them with suggestive names so we can keep track of them. Okay, so now in order to calculate what's going on here, we have to get our differential equations. So let's say, oh, x is going to be, remember, coming into this is a value of z. Coming out is z dot. So we're going to have to calculate a z dot from the equations of motions and so on. So we have to calculate 4 numbers, which is the rate of change of the x's and v's, right? And in fact, let me just put the last line in here. It's going to be x dot as a list of 2 numbers, and then v dot, a list of 2 numbers, and then this is a list of 4 numbers, which we don't know what these, I haven't calculated these numbers yet, but it's going to be 4 numbers we're going to get in here, the 2 x's and so on. So let's say the initial values of x is what? The first 2 values of z. So that's z, and then the first 2 values are 1, colon 2, if you like that. And that's the first 2 values of z. And then I have the second 2 values are v, and that's going to be v is going to be z, is the second 2 values, z sub 3 colon 4. So now, coming into this, I'm getting 4 values which are representing x1, x2, x3, x4. Coming out are going to be 4 values, the rate of change. But in between, I want to think about x and v so I can write the laws of mechanics and so on. So for example, the second set of differential equations, how the v's change, the first set of differential equations, how the x's change is x dot equals v. So of the 4 differential equations, this is the first 2 of them. So half of the crystal ball, seeing how x evolves in time, is just using the simple kinematic relation that the rate of change of the x's is the v's. And that's what's going to be used in Euler's method to update the x's as the current value of v's. Now we have to update the v's. So how do we update the v's? Well, we have v1 dot came from some big expression divided by m1. And m1 we'll assume is called p dot m1. And now what was that big expression for m1? It was t2s, t2s plus t, get that thing readable, t2 dash pot minus t1. I haven't figured out what those tensions are yet, but I don't want to do all that substitution in here because I don't want to make this thing too hard to read. And then I have v2 dot is equal to t3 minus t2d minus t2s, and then this is all divided by the mass of mass 2. And I have I want here a minus sign instead of an equal sign. Is that right? T3 minus T2d dot dot, and I've got 2 parentheses where I only want 1 parenthesis. Okay, so that tells me the rate of change of these v's if only I knew what these tensions were. So I can calculate these tensions somewhere. To keep all the differential equations in one place, I'll just put those all in a line there. So here's all 4 of my ODEs. Here's the next 2 ODEs. And then we're all done except for I've got to figure out what v dot here. And I could just put v, well, there's various ways to do it. When in doubt, I guess my suggestion is put more lines of code which are shorter because it's easier to debug it and figure out what's going on. It's easier to read it. So v dot is a mixture of v1 dot and v2 dot. And then I've got this ready to go. So all I've got to figure out now is what these t's are, and I've got my whole right-hand side. Okay, so what are these t's? Well, T1, which was the first tension, which was pulling the first thing back, was equal to K1, which I'm going to say P dot K1, times X1, and that's X1 like this, or I could have made a new variable called X1, which was X sub 1, minus X0, which means, oops, I've got to calculate what X0 is. And then I have minus the length of that, the initial length of that, which was P dot L0. And L is an unfortunate variable because it's hard to keep it straight from 1, which looks like that. So that's going to be a hard thing to debug if we make a mistake in that way. Okay, so now I've got a problem that I didn't say what X0 was. So X0 is equal to D, which we'll call P dot D, times cosine of omega, which I'll call P dot omega, times the value of T that comes into this. So now, assuming I've got T coming into this, and the omega coming into this, and D coming into this, then I've calculated what X0 is. So I've got everything I need to calculate T1. Anybody, any questions so far? Anybody want me to repeat something? Yeah?
I thought on the board it said that X0 was sine.
I intended cosine in the picture, so if I wrote sine, it was a mistake. Because not that it matters much for our purposes here, but if I wanted it, I intended it to be when the motor was sticking to the right, we had a value of D. Yes?
Would you need a more descriptive name for L naught because there's more than one L naught in the system?
Yeah, so let me, where was that? P dot L, actually, okay, so it was, let's say L10, yeah? How about that? Is that nicer? Okay, so there's L10, and that's the only place I've used it here. Okay, now I need to get T2, and I need to get T3. T2S, T2 damper, and T3. Okay, so we have to tediously fill in the stuff that was on the blackboard. What was T2S? It was P dot K2 multiplied by, notice here I'm missing a times. How many people saw that and didn't tell me? Okay. P2, the second spring is what? It's the length of that spring, which was X sub 2 minus the quantity X sub 1 plus W1, which is P dot W1 minus the length of rest length of spring 2, which is P dot L20, and that's altogether the tension of spring 2. Then we have this, the tension, the dash pot, which was P dot C2, and we have to multiply by the expansion rate of that dash pot, and that was V sub 2 minus V sub 1. And then we have the third tension, which was P dot K3 times, and then we have the length of the third spring, which is the current length, which is L minus, and what is L? We've got to call that P dot L if we're passing it all in here, minus X sub 2 plus P dot W2. That's the position of the right-hand edge of block 2. So this is the length of the spring 2 minus P dot L20. No, P dot L 30. Okay, now do you want to stare at any one of these equations or ask me to talk through any one of them, or does any of you see a mistake in any of them? Or some part of one that you don't understand, so it might be a mistake. Yes?
How come in Q1 you have like x0 without parentheses and all the other like?
Because some of these things are the state variables which we're trying to calculate, and some of them are given to us. So if we know the time and we know the parameters, we are told explicitly what x0 is. We don't have to solve for it from the differential equation. So it's not something we're using our crystal ball to calculate, it's given to us. So x0 we're just calculating, it's not being passed back and forth as part of the ODE solution. So when you say that if you know the time and the state, we know what the forcing is, that means that we have some given forcing function as a function of time, which we do in this case, which is this motion of this left-hand edge powered by this motor. Does that address your question? Another question. Just out of curiosity, how many people appreciated that question? Raise your hands. Several did, just for future reference. Okay, so now the claim is this whole package here is the crystal ball. Or if we want to think of it, there's two players that are predicting the future together. There's you and there's me. You're going to tell me what the state of the world is. I'm going to tell you its rate of change. And you're going to ask me that whenever you want. And I have just done my part of the job, which is I've agreed to answer your question whenever you want. You tell me what z is, which means the x's and v's. I'll tell you the rates of change. And I'm going to package them all in this list of 4 numbers. And I've done my job. Now the whole crystal ball has 2 parts. It's that part plus Euler's method, where we use that repeatedly to predict the future. So this is the one part. The second part is Euler's method, which I've now coded up here very compactly. And the key line is this line right here. We're going to predict the future by looking at the present, looking ahead a little bit, multiplying by a little bit of time, and that gives us a new value. And then we're going to cycle through a loop again and again to predict the future. Yes?
Where are you assigning the values that
That's way up here. I didn't do that yet. But I'm going to, as far as Euler's method is concerned, I will have calculated those at the top of the program. I'm going to use my right-hand side function. You're going to use the right-hand side function. And you are going to ask me, please tell me the rates of change of everything. I am going to do it by taking the current values of time, z, and the parameters. I'm going to run this program, and I'm going to tell you the rates of change of everything. Then you're going to have access to it back up here. That's the z dot. And then you're going to step forward in time a little bit to predict the future a little bit. And then you're going to do that again and again and again. Okay? I call this thing T array, so I went T array sub n plus 1. Okay, so now let's read this Euler's method. How does it go? We start out with some value of z nu, which has been assigned to us, which we start up here. So we're going to start out at some initial value. Here I've just zeroed some memory to make space up for it. The MATLAB works without this command. It just works much slower. I'm going to say the first value of these arrays are the starting values. I've got, now I'll say z, the current value of z is the new value. The current value of t is the new value. I calculate the rates of change using that big function we just wrote. I advance in time to get new values for all the things. I advanced in time to get new value for the time. I haven't showed you, but I picked ahead of time an array of times that I want to solve at. Yes? At the end of the program, it's going to break something. So I.
Well, no, I mean, the first time you gotta run it, and it's going to be larger than the array size.
I want I. Is that what you're saying? I looks good. See what the confusion was. Then I have, I assign new value to the T array. I don't really have to do that because I've actually done that on the top. And then I have the new values for Z, which I'm going to store in an array. Here's one slightly confusing thing, is we have a list of 4 numbers, which is the values of x's and v's at one time. And we want to store that list at lots of times. So we have a list of lists. That's a 2-dimensional array. And we have to make a decision about whether to make time be the rows of that array or the columns. Because we're going to later use MATLAB subroutines for differential equations, and they have their convention, we'll copy their convention. And that list of numbers, x1, x2, x3, x4, or z1, z2, z3, z4, we're going to think of as a row. And so we're going to pick, we're going to have this row of numbers. So we say the ith row, all the elements of it, are these list of these 4 numbers. So this makes an array, each row of which is x1, x2, v1, v2 at some time. And the next row is the next time, and so on. Okay, now we need to get all these parameters in, and I got partway through putting these parameters in, but I didn't get them all in. So let's see, we start out here with clear all. We've got our initial conditions. Now the initial conditions are a little more complicated than they were before, because we have 2 values for x to have initial conditions. So this is x1 and x2. And we have 2 values of v for initial conditions. That's v1 and v2. And then down over here, where we start the thing off, this ODE solver, we need 4 numbers. So we put these 2 numbers next to these 2 numbers, and this makes a list of 4 initial conditions. So this is the 4 initial conditions. Okay, going back up here, now we've got our parameters, p.m1, p.m2, p.k1, p.k2, p.k3. I've set them all equal to 1, so it's less confusing to read. I've got my damping. I made it kind of small. I've got my step size. I picked it whatever I wanted it to be, but actually I assign it again below, so let me make that not confusing. I've got my omega, which I just picked. This is leftover from the last program. We'll do what we want with that. I've got my d here, and that should be p.omega. And I've got my d here, which should be p.d. And I'm missing some parameters. I haven't got them all in here, right? What did I miss? I missed p.w1, and let's just make that 0 so that it corresponds more like the homework. We'll just assume that things are all on top of each other. And I've got p.w2, so this mass has 0 width, just to keep it simple. And I've got my total length, which is stretching this thing all the way across. Let me say, just for simplicity, let me make that 0. I've got all my rest lengths of my springs, which is p.l10, and that had to equal something. Let's just make it 0. Why 0? Because it puts everything on top of each other, and it makes it so we don't have all these extra constants that look funny in the solution. And I've got the same thing for my 2, 0 and my 3, 0. If they're not 0, everything is fine. Say again? My total length, you're saying I've forgotten it. p.l. Okay. Anybody think of another parameter I might have left off? Yes? Where do you want my semicolon? This one here? Well, I'm missing it there. In the for loop is a bad place to be missing a semicolon, because it'll print and print and print, and the printing takes longer than calculating, and it'll fill up your screen, and you'll be waiting for the computer. Yes? That's right. Well, whatever I put here is a different problem, right? I can start it any way I want.
It seems like you do it the way we set it up.
I can do what I want over there, right? So can you see that? Can you see this Is it light enough for you to see this right now? Let's pretend this is the rest position. So we're doing it from the rest position. I can then start it here like that, and then let go.
Right, but can you move that car to the other side of it?
Oh, because my rest lengths were 0, you mean? This is a mathematical detail. The way, if I, yes, you're right. In the math, since I set this width equal to 0, and I set this width equal to 0, and I set this rest length equal to 0, the rest position, the two are on top of it.
Isn't that the position, not the length? So that's the distance from the core. So you're saying that. So like, I think the way you have it set up is that the right car is actually the left car.
That's right.
But they're opposite.
That's right.
Okay.
So in the math of this thing, I've got the right one to the left. I've got the right one, the left one to the right of the right one. That's what the math says. Now, had I put in all these different lengths and w's and so on, and had I put in my x0 was something plus this thing, everything would have been fine. But what I did is I set all those constants equal to 0, the rest length and the widths and so on, to keep the math simple and to keep it so the solution of this problem would correspond to the solution of, say, the problem you did for homework, where you just measured relative to the rest positions. So in effect, I've made it so my x's are the positions relative to the rest positions. I've done that in effect. Or if you like, we're living in an abstract world where things can pass through each other, if that helps you, if that works better for you. Okay? Yes, I could have been more physical had I put in non-zero values for all these things and made this x be a little bit bigger than x0 plus L10 and so on. And that would have been more physical. The graphs would have had offsets in them. But I'm doing this for debugging, making the code look simpler and so on. But maybe I confused you. There is always the problem that shortcuts are confusing. Perpetual problem. Okay. Anybody want me to talk through any of this code again, or go through it from top to bottom, or should we just run it and find the mistakes? Yes?
You assign values to key array using linspace function.
Oh,
A little bit above, but then you overwrote key array with the zeros array, and the first value was key.
That's a very good mistake. Okay, so linspace function, does anybody not know what this one is? Okay, you all know what that is. Then I overwrote my T array with zeros somewhere, and I don't need that anymore. And I'm not going to even assign values to T array because I'm just going to have it pre-calculated. So here what I've done, I didn't talk through this part of the program, so let me talk it through now. I'm going to specify a starting time, an ending time, a step size, how big I'm going to step through in time. I'm going to divide up the interval into the length divided by the size of the step sizes. That's n, and I put floor here to make it an integer. Then I'm going to make an array of t values which start at this value, end at this value, and there are this many of them. So I'm pre-calculating all the times that I'm going to solve the differential equation. And the reason I'm doing this is because it corresponds more to the way that the ODE 4.5, the program we're going to learn, does things. Okay, thank you for that. Okay, let's see what mistakes I have. Cool. Now, it is possible that there are not mistakes here. Or it could be that we're seeing is nonsense. Now, see, it's growing in time. That looks bad to me, but maybe that growing in time is because I didn't take a small enough time step. Still growing in time. That looks bad to me, except maybe it's resonating. So let's just see. Maybe it's shaking the thing, and that's making it grow in time. Aha! So there it is without the forcing. Okay, so let's try it without the forcing, and let's try a really cool initial condition, which is 1 minus 1. So So if I take this thing, can you see this with the lights off? Yes? If I turn the lights on, I'm not going to be able to turn them off properly. Okay, I find the equilibrium position of these things, and then I move them equal distances to the right and left. And it does this cool, simple sinusoidal motion. Now another cool one I can do is I move them equal distances to the right. And it crashes into the thing. I move them equal distances to the right, and it does this cool motion. Or I can start them from 0, and I can turn on the motor. Wishful thinking. There's a motor switch somewhere. And this thing starts oscillating at some frequency. And it's been picked just right, so I was told, to do something interesting, but it wasn't picked just right to do something interesting. Okay, is there some feature of the solutions or the setup that you would have questions about? So the claim is, if I force that at just the right frequency, and I start it at, say, 0 and 0, what would be just the right frequency? In this case, it turns out 1 is one of the just right frequencies. I put in just a small displacement here, and then I run this thing, I get resonance. So even though this has 2 degrees of freedom, I get a resonance by forcing it at the right frequency. There's another cool frequency I can set this to, which is about. Does anybody know what the other cool frequency is? What? I think it's the square root of 3. Then I get something. Nope, wasn't square root of 3. Square root of 2, I have to calculate it. I think I'll pick this up again quickly next time, but not do all the review next time, and then we'll go on to something else. Okay.